6. Application of derivatives. In this chapter, we will study applications of the derivative in various disciplines, for example, in engineering, science, social science, and many other fields. For instance, we will learn how the derivative can be used. Number 1. To determine rate of change of quantities. Number 2. To find the equations of tangent and normal to a curve at a point. Number 3. To find turning points on the graph of a function, which in turn will help us to locate points at which largest or smallest value locally of a function occurs. We will also use derivative to find intervals on which a function is increasing or decreasing. Finally, we use the derivative to find approximate value of certain quantities. Rate of change of quantities. The derivative ds by dt, we mean the rate of change of distance s with respect to the time t. In a similar fashion, whenever one quantity y varies with another quantity x, satisfying some rule y is equal to f of x, then dy by dx or f dash of x represents the rate of change of y with respect to x, and dy by dx at x is equal to x0 or f dash of x0 represents the rate of change of y with respect to x at x is equal to x0. Further, if two variables x and y are varying with respect to another variable t, that is, if x is equal to f of t and y is equal to g of t, then by chain rule, dy by dx is equal to dy by dt upon dx by dt. If dx by dt is not equal to 0, thus the rate of change of y with respect to x can be calculated using the rate of change of y and that of x both with respect to t. Example 1. The radius of a circle is increasing uniformly at the rate of 3 cm per second. Find the rate at which the area of the circle is increasing when the radius is 10 cm. Solution. The area of a circle with radius r is given by a is equal to pi r square, where r is equal to radius of circle. The radius of a circle is increasing at the rate dr by dt is equal to 3 cm per second. dA by dt is equal to d by dt pi r square is equal to d by dr pi r square into dr by dt is equal to 2 pi r dr by dt is equal to 2 pi into 10 into 3 is equal to 60 pi centimeter square per second. Hence, the rate of circle is increase of area of a circle is 60 pi centimeter square per second. Example 2. An age of a variable cube is increasing at the rate of 3 centimeter per second. How fast is the volume of the cube increasing when the age is 10 centimeter long? Solution. Let the age of a cube be x centimeter. Therefore, the volume of a cube is v is equal to x cube. Given that dx by dt is equal to 3 centimeter per second, v is equal to x cube. Therefore, dv by dt is equal to d by dt x cube is equal to d by dt x cube into dx by dt is equal to 3x square into 3 is equal to 9x square is equal to 9 into 10 square because of x is equal to 10 centimeter is equal to 900 centimeter cube per second. Hence, the volume of the cube is increases at the rate of 900 centimeter cube per second. Example 3. The length x of a rectangle decreasing at the rate of 5 centimeter per minute and the width y is increasing at the rate of 4 centimeter per minute. When x is equal to 8 centimeter and y is equal to 6 centimeter, find rate of change of A, the perimeter, and B, the area of the rectangle. Solution. The length of a rectangle is x centimeter and its width is y centimeter. Given that dx by dt is equal to minus 5 centimeter per minute, dy by dt is equal to 4 centimeter per minute. Perimeter of a rectangle P is equal to 2x plus 2y. Therefore, dp by dt is equal to d by dt 2x plus 2y is equal to 2 dx by dt plus 2 dy by dt is equal to 2 into minus 5 plus 2 into 4 is equal to minus 10 plus 8 is equal to minus 2 centimeter per minute. Hence, the perimeter is decreases at the rate of 2 centimeter per minute. Area of a rectangle A is equal to xy. Therefore, dA by dt is equal to d by dt xy is equal to x dy by dt plus y dx by dt. Therefore, dA by dt is equal to 8 into 4 plus 6 into minus 5. Because of x is equal to 8 centimeter, y is equal to 6 centimeter is equal to 32 minus 30 is equal to 2 centimeter square per minute. Therefore, the area of a rectangle is increases at the rate of 2 centimeter square per minute. Increasing and decreasing functions. In this section, we will use differentiation to find out whether a function is increasing or decreasing or none. Consider the function f given by f of x is equal to x square, where x belongs to R. The graph of this function is a parabola as given in figure. First, consider the graph to the right of the origin. Observe that as we move from left to right along the graph, the height of the graph continuously increases. For this reason, the function is said to be increasing for the real numbers x is greater than 0. Now consider the graph to the left of the origin and observe here that as we move from left to right along the graph, the height of the graph continuously decreases. Consequently, the function is said to be decreasing for the real numbers x is less than 0. Definition 1. Let I be an interval contained in the domain of a real valued function f. Then f is said to be number 1 increasing on I if x1 is less than x2 in I, which implies that f of x1 is less than or equal to f of x2 for all x1, x2 belongs to I. Number 2, decreasing on I if x1, x2 in I, which implies that f of x1 is less than f of x2 for all x1, x2 belongs to I. Number 3, constant on I if f of x is equal to c for all x belongs to I, where c is a constant. Number 4, decreasing on I if x1 is less than x2 in I, which implies that f of x1 is greater than or equal to f of x2 for all x1, x2 belongs to I. Number 5, strictly decreasing on I if x1 is less than x2 in I, which implies that f of x1 is greater than f of x2 for all x1, x2 belongs to I. For graphical representation of such functions, see figure. Definition 2. Let x0 be a point in the domain of definition of a real valued function f. Then f is said to be increasing, decreasing at x0 if there exists an open interval I containing x0 such that f is increasing, decreasing respectively in I. Example 1. Show that the function given by f of x is equal to 3x plus 17 is increasing on R. Solution: f of x is equal to 3x plus 17. Therefore, f dash of x is equal to 3 is greater than 0. For any value in R, f dash of x is greater than 0. Therefore, the function f of x is strictly increasing on R. Theorem 1. Let f be continuous on closed interval a, b and differentiable on the open interval a, b. Then f is increasing in closed interval a, b if f dash of x is greater than 0 for each x belongs to open interval a, b. F is decreasing in closed interval a, b if f dash of x is less than 0 for each x belongs to open interval a, b. C. F is a constant function in closed interval a, b if f dash of x is equal to 0 for each x belongs to open interval a, b. Proof. Let x1, x2 belongs to closed interval a, b be such that x1 is less than x2. Then, by mean value theorem, there exists a point C between x1 and x2 such that f of x2 minus f of x1 is equal to f dash of C into x2 minus x1. That is, f of x2 minus f of x1 is greater than 0 because f dash of C is greater than 0 given. That is, f of x2 is greater than f of x1. Thus, we have x1 is less than x2, which implies that f of x1 is less than f of x2 for all x1, x2 belongs to closed interval a, b. Hence, f is an increasing function in closed interval a, b. Remark: there is a more generalized theorem which states that if f dash of x is greater than 0 for x in an interval, excluding the endpoints, and f is continuous in the interval, then f is increasing. Similarly, if f dash of x is less than 0 for x in an interval, excluding the endpoints, and f is continuous in the interval, then f is decreasing. Example 1. Show that the function f given by f of x is equal to x cube minus 3x square plus 4, where x belongs to R, is increasing on R. Solution: f dash of x is equal to 3x square minus 6x plus 4 is equal to 3 into x square minus 2x plus 1 is equal to 3 into x minus 1 whole square plus 1 is greater than 0 in every interval of R. Therefore, the function f is increasing on R. Example 2. Show that the function f of x is equal to sin x. A. Increasing in open interval 0 to pi by 2. B. Decreasing in open interval pi by 2 to pi. C. Neither increasing nor decreasing in open interval 0 to pi. Solution: f of x is equal to sin x. Therefore, f dash of x is equal to cos x. A. Open interval 0 2 pi by 2 is a first quadrant. In open interval 0 to pi by 2, cos x is greater than 0. Therefore, f dash of x is greater than 0. Therefore, in open interval 0 to pi by 2, the function f of x is strictly increasing. B. Open interval pi by 2 to pi is a second quadrant. In open interval pi by 2 to pi, cos x is less than 0. Therefore, f dash of x is less than 0. Therefore, in open interval pi by 2 to pi, the function f of x is strictly decreasing. C. Open interval 0 to pi represents the first and second quadrant. For all x belongs to open interval 0 to pi, we cannot decide that cos x is positive or negative. For some value of x, cos x is greater than 0, and for some value of cos x is less than 0. Therefore, the function f of x is neither increasing or decreasing in open interval 0 to pi. Example 3. Find the intervals in which the function f given by f of x is equal to 2x square minus 3x is a. Strictly increasing, b. Strictly decreasing. Solution: f of x is equal to 2x square minus 3x. Therefore, f dash of x is equal to 4x minus 3. If f dash of x is equal to 0, then x is equal to 3 by 4. X is equal to 3 by 4 divides the number line in two parts. 4x minus 3 is less than 0, open interval, minus infinity to 3 by 4 interval, and open interval 3 by 4 to infinity interval. When x belongs to open interval minus infinity to 3 by 4, 4x minus 3 is less than 0. Therefore, f dash of x is less than 0. Therefore, f of x is strictly decreasing in open interval minus infinity to 3 by 4. When x belongs to open interval 3 by 4 to infinity, 4x minus 3 is greater than 0. Therefore, f dash of x is equal to 0. Therefore, f of x is strictly increasing in open interval 3 by 4 to infinity. And normals. In this section, we shall use differentiation to find the equation of the tangent line and the normal line to a curve at a given point. The equation of a straight line passing through a given point x0, y0 having finite slope m is given by y minus y0 is equal to m into x minus x0. Note that the slope of the tangent to the curve y is equal to f of x at the point x0, y0 is given by dy by dx at x0, y0 is equal to f dash of x0. So, the equation of the tangent at x0, y0 to the curve y is equal to f of x is given by y minus y0 is equal to f dash of x0 into x minus x0. Also, since the normal is perpendicular to the tangent, the slope of the normal to the curve y is equal to f of x at x0, y0 is minus 1 upon f dash of x0. If f dash of x0 is not equal to 0, therefore, the equation of the normal to the curve y is equal to f of x at x0, y0 is given by y minus y0 is equal to minus 1 upon f dash of x0 into x minus x0 is equal to 0. That is, y minus y0 into f dash of x0 plus x minus x0 is equal to 0. Note, if a tangent line to the curve y is equal to f of x, makes an angle theta with x-axis in the positive direction, then dy by dx is equal to slope of the tangent is equal to tan theta. Particular cases. Number 1. If slope of the tangent line is 0, then tan theta is equal to 0 and so theta is equal to 0, which means the tangent line is parallel to the x-axis. In this case, the equation of the tangent at the point x0, y0 is given by y is equal to y0. Number 2. If theta tends to pi by 2, then tan theta tends to infinity, which means the tangent line is perpendicular to the x-axis, that is parallel to the y-axis. In this case, the equation of the tangent at x0, y0 is given by x is equal to x0. Example 1. Find the slope of the tangent of the curve y is equal to 3x raised to 4 minus 4x at x is equal to 4. Solution. Equation of the curve y is equal to 3x raised to 4 minus 4x. Slope of tangent to the curve at one point x, y is equal to dy by dx. Therefore, dy by dx is equal to d by dx 3x raised to 4 minus 4x is equal to 12x cube minus 4. Therefore, dy by dx at x is equal to 4 is equal to 12 into 4 cube minus 4 is equal to 764. Therefore, the slope of the tangent to the curve at x is equal to 4 is 764. Example 2. Find the slope of the normal of the curve x is equal to 1 minus a sin theta, y is equal to b cos square theta at theta is equal to pi by 2. Solution. Slope of tangent to the curve at a point x, y is equal to dy by dx. X is equal to 1 minus a sin theta, y is equal to b cos square theta. Theta is equal to pi by 2. Therefore, dx by d theta is equal to minus a cos theta. dy by d theta is equal to minus 2b cos theta sin theta. Therefore, dy by dx is equal to dy by d theta upon dx by d theta is equal to minus 2b cos theta sin theta upon minus a cos theta is equal to 2b sin theta upon a. The slope of the tangent at the point x, y of the curve is equal to dy by dx. The slope of the tangent at point theta is equal to pi by 2 is equal to dy by dx at theta is equal to pi by 2 is equal to 2b sin pi by 2 upon a is equal to 2b upon a because of sin pi by 2 is equal to 1. Therefore, the slope of the normal at point theta is equal to pi by 2 is equal to minus 1 upon slope of tangent is equal to minus 1 upon 2b upon a is equal to minus a upon 2b. Approximations. Let f from D to R, where D is a subset of R, be a given function, and let y is equal to f of x. Let delta x denote a small increment in x. Recall that the increment in y corresponding to the increment in x denoted by delta y is given by delta y is equal to f of x plus delta x minus f of x. We define the following. Number 1. The differential of x denoted by dx is defined by dx is equal to delta x. Number 2. The differential of y denoted by dy is defined by dy is equal to f dash of x dx, or dy is equal to dy by dx delta x. In case dx is equal to delta x is relatively small, When compared with x, dy is a good approximation of delta y, and we denote it by dy approximately equal to delta y. For geometrical meaning of delta x, delta y, dx and dy, one may refer to figure. Example 1. Use differential to approximate square root of 25.3. Solution. Suppose y is equal to square root of x is equal to x raised to 1 upon 2. Taking x is equal to 25 and delta x is equal to 0.3. Delta y is equal to x plus delta x whole raised to 1 upon 2 minus x raised to 1 upon 2 is equal to 25 plus 0.3 whole raised to 1 upon 2 minus 25 raised to 1 upon 2 is equal to 25.3 raised to 1 upon 2 minus 5. Therefore, 25.3 raised to 1 upon 2 is equal to delta y plus 5. Now, dy is approximately equal to delta y. Therefore, dy is equal to dy by dx into delta x is equal to d by dx x raised to 1 upon 2 into delta x is equal to 1 upon 2 into x raised to 1 upon 2 into delta x is equal to 1 upon 2 into 25 raised to 1 upon 2 into 0.3 is equal to 0.3 upon 10. Therefore, delta y is equal to 0.03. Thus, the approximate value of square root of 25.3 raised to 1 upon 2 is equal to delta y plus 5 is equal to 0.03 plus 5 is equal to 5.03. Example 2. Find the approximate value of f of 5.001 where f of x is equal to x cube minus 7x square plus 15. Solution. F of x is equal to x cube minus 7x square plus 15. Therefore, f dash of x is equal to 3x square minus 14x. Now, delta y is equal to f of x plus delta x minus f of x. Therefore, f of x plus delta x is equal to f of x plus delta y is equal to f of x plus f dash of x into delta x because of dx is equal to delta x. Taking x is equal to 5 and delta x is equal to 0.001. F of 5 plus 0.001 is equal to f of 5 plus f dash of 5 into 0.001. Therefore, f of 5.001 is equal to 5 cube minus 7 into 5 square plus 15 plus 3 into 5 square minus 14 into 5 into 0.001 is equal to 125 minus 175 plus 15 plus 75 minus 70 into 0.001 is equal to minus 35 plus 0.005 is equal to minus 34.995. Example 3. If the radius of a sphere is measured as 7 meter with an error of 0.02 meter, then find the approximate error in calculating its volume. Solution. Suppose r be the radius of the sphere. Now, the volume V of the sphere is given by V is equal to 4 by 3 pi r cube. Therefore, dV by dr is equal to d by dr 4 by 3 pi r cube is equal to 4 pi r square. There is an error of 0.02 meter in the measure of radius. Delta r is equal to 0.02 meter and radius r is equal to 7 meter. Approximate error in calculating the volume of the cube delta V is equal to dV upon dr into delta r is equal to 4 pi r square into delta r is equal to 4 pi into 7 square into 0.02 is equal to 3.92 pi meter cube. Maxima and minima. In this section, we will use the concept of derivatives to calculate the maximum or minimum values of various functions. In fact, we will find the turning points of the graph of a function and thus find points at which the graph reaches its highest or lowest locally. The knowledge of such points is very useful in sketching the graph of a given function. Further, we will also find the absolute maximum and absolute minimum of a function that are necessary for the solution of many applied problems. Let us consider the following problems that arise in day-to-day life. Number 1. The profit from a grove of orange trees is given by P of x is equal to ax plus bx square, where a, b are constants and x is the number of orange trees per acre. How many trees per acre will maximize the profit? Number 2. An Apache helicopter of enemy is flying along the path given by the curve f of x is equal to x square plus 7. A soldier placed at the point 1, 2 wants to shoot the helicopter when it is nearest to him. What is the nearest distance? In each of the above problem, there is something common, that is, we wish to find out the maximum or minimum values of the given functions. In order to tackle such problems, we first formally define maximum or minimum values of a function, points of a local maxima and minima, and test for determining such points. Definition 3. Let f be a function defined on an interval I. Then f is said to have a maximum value in I if there exists a point C in I such that f of C is greater than or equal to f of x for all x belongs to I. The number f of C is called the maximum value of f in I, and the point C is called a point of maximum value of f in I. B. F is said to have a minimum value in I if there exists a point C in I such that f of C is less than or equal to f of x for all x belongs to I. The number f of C in this case is called the minimum value of f in I, and the point C in this case is called a point of minimum value of f in I. C. F is said to have an extreme value in I if there exists a point C in I such that f of C is either a maximum value or a minimum value of f in I. The number f of C in this case is called an extreme value of f in I, and the point C is called an extreme point. Remark: in figure, we have exhibited that graphs of certain particular functions help us to find maximum value and minimum value at a point. In fact, through graphs, we can even find maximum or minimum value of a function at a point at which it is not even differentiable. Example 1. Find the function f of x is equal to 2x minus 1 whole square plus 3, which has maximum and minimum values. Solution: f of x is equal to 2x minus 1 whole square plus 3. Therefore, f dash of x is equal to 2 into 2x minus 1 into 2 is equal to 4 into 2x minus 1 is equal to 8x minus 4. F double dash of x is equal to 8. For maximum or minimum value, f dash of x is equal to 0. Therefore, 8x minus 4 is equal to 0. Therefore, x is equal to 1 upon 2. Now, f double dash of 1 upon 2 is equal to 8 is greater than 0. Therefore, f of x has minimum value at x is equal to 1 upon 2. Minimum value of the function is equal to f of 1 upon 2 is equal to 2 into 1 upon 2 minus 1 whole square plus 3 is equal to 3. It is clear that the function has no maximum value. Example 2. Find the maximum and minimum values of f if any of the function given by f of x is equal to modulus of x, where x belongs to R. Solution. From the graph of the given function, note that f of x is greater than or equal to 0 for all x belongs to R, and f of x is equal to 0 if x is equal to 0. Therefore, the function f has a minimum value 0 and the point of minimum value of f is x is equal to 0. Also, the graph clearly shows that f has no maximum value in R and hence no point of maximum value in R. Note number 1. If we restrict the domain of f to closed interval minus to 1 only, then f will have maximum value modulus of minus 2 is equal to 2. Number 2. One may note that the function f in example 2 is not differentiable at x is equal to 0. Every continuous function f on a closed interval has a maximum and a minimum value. Maximum and minimum values of a function defined on a closed interval will be discussed later in this section. Let us now examine the graph of a function as shown in figure. Observe that at points A, B, C and D on the graph, the function changes its nature from decreasing to increasing or vice versa. These points may be called turning points of the given function. Further, observe that at turning points, the graph has either a little hill or a little valley. Roughly speaking, the function has minimum value in some neighborhood interval of each of the points A and C, which are at the bottom of their respective valleys. Similarly, the function has maximum value in some neighborhood of points B and D, which are at the top of their respective hills. For this reason, the points A and C may be regarded as points of local minimum value or relative minimum value, and points B and D may be regarded as points of local maximum value or relative maximum value for the function. The local maximum value and local minimum value of the function are referred to as local maxima and local minima respectively of the function. Definition 4. Let f be a real valued function and let C be an interior point in the domain of f, then A. C is called a point of local maxima if there is an h is greater than 0 such that f of C is greater than or equal to f of x for all x in open interval C minus h, C plus h, where x is greater than or equal to C. The value f of C is called the local maximum value of f. B. C is called a point of local minima if there is an h is greater than 0 such that f of C is less than or equal to f of x for all x in open interval C minus h, C plus h. The value f of C is called the local minimum value of f. Geometrically, the above definition states that if x is equal to c is a point of local maxima of f, then the graph of f around c will be as shown in figure. Note that the function f is increasing, that is f dash of x is greater than 0 in the interval open interval c minus h c, and decreasing, that is f dash of x is less than 0 in the interval open interval c plus h. This suggests that f dash of c must be 0. Similarly, if c is a point of local minima of f, then the graph of f around c will be as shown in figure. Here f is decreasing, that is f dash of x is less than 0 in the interval open interval c minus h c, and increasing, that is f dash of x is greater than 0 in the interval open interval c plus h. This again suggests that f dash of c must be 0. Theorem 2. Let f be a function defined on an open interval I. Suppose c belongs to I be any point. If f has a local maxima or a local minima at x is equal to c, then either f dash of c is equal to 0 or f is not differentiable at c. Note, a point in the domain of a function f at which either f dash of c is equal to 0 or f is not differentiable is called a critical point of f. Theorem 3. First derivative test. Let f be a function defined on an open interval I. Let f be continuous at a critical point c in I. Then, number 1, if f dash of x changes sign from positive to negative as x increases through c, that is, if f dash of x is greater than 0 at every point sufficiently close to and to the left of c, and f dash of x is less than 0 at every point sufficiently close to and to the right of c, then c is a point of local maxima. Number 2, if f dash of x changes sign from negative to positive as x increases through c, that is, if f dash of x is less than 0 at every point sufficiently close to and to the left of c, and f dash of x is greater than 0 at every point sufficiently close to and to the right of c, then c is a point of local minima. Number 3, if f dash of x does not change sign as x increases through c, then c is neither a point of local maxima nor a point of local minima. In fact, such a point is called point of inflection. Example 1. Find the maximum and minimum values of the function f of x is equal to sin 2x plus 5. Solution: f of x is equal to sin 2x plus 5. We know that minus 1 is less than or equal to sin 2x is less than or equal to 1. Therefore, minus 1 plus 5 is less than or equal to sin 2x plus 5 is less than or equal to 1 plus 5. Therefore, 4 is less than or equal to f of x is less than or equal to 6. Therefore, f of x has maximum value 6 and minimum value 4. Function f of x has a maximum value of 6 and a minimum value of 4. Example 2. Of all the closed cylindrical cans, write circular of a given volume of 100 cubic centimeters. Find the dimensions of the can which has the minimum surface area. Solution: let the height of a cylindrical can be h centimeter and the radius of its base is r centimeter. Therefore, its volume V is equal to pi r square h is equal to 100 cubic centimeter. Therefore, h is equal to 100 upon pi r square. Equation 1. If S is the total surface area of the cylindrical cans, S is equal to 2 pi RH plus 2 pi R square. Therefore, S is equal to 2 pi R into 100 upon pi R square plus 2 pi R square because of from equation 1. Therefore, S is equal to 200 upon R plus 2 pi R square. Therefore, ds by dr is equal to minus 200 upon R square plus 4 pi R, and d square s upon dr square is equal to 400 upon R cube plus 4 pi. For minimal surface area, ds by dr is equal to 0. Minus 200 upon R square plus 4 pi R is equal to 0. Therefore, 4 pi R is equal to 200 upon R square. Therefore, R cube is equal to 200 upon 4 pi is equal to 50 upon pi. Therefore, R is equal to 50 upon pi raised to 1 upon 3 centimeter. D square s by dr square at R is equal to 50 upon pi raised to 1 upon 3 is equal to 400 upon 50 into pi plus 4 pi is equal to 12 pi is greater than 0. Therefore, S is minimal when R is equal to 50 upon pi raised to 1 upon 3. H is equal to 100 upon pi R square is equal to 100 upon pi into 50 upon pi raised to 2 by 3 is equal to 2 into 50 upon pi raised to 1 upon 3 centimeter. Therefore, radius R is equal to 50 upon pi raised to 1 upon 3 and height h is equal to 2 into 50 upon pi raised to 1 upon 3 centimeter. Theorem 4. Second derivative test. Let f be a function defined on an interval I and c belongs to I. Let f be twice differentiable at c. Then number 1, x is equal to c is a point of local maximum if f dash of c is equal to 0 and f double dash of c is less than 0. The value f of c is local maximum value of f. Number 2, x is equal to c is a point of local minima if f dash of c is equal to 0 and f double dash of c is greater than 0. In this case, f of c is the local minimum value of f. Number 3, the test fails if f double dash of c is equal to 0 and f dash of c is equal to 0. In this case, we go back to the first derivative test and find whether c is a point of local maximum, local minimum, a point of inflection. Example 1. Find the local maxima and local minima value of f of x is equal to x cube minus 6x square plus 9x plus 15. Solution: f of x is equal to x cube minus 6x square plus 9x plus 15. Therefore, f dash of x is equal to 3x square minus 12x plus 9. F double dash of x is equal to 6x minus 12. For local maxima or minima values, f dash of x is equal to 0. Therefore, 3x cube minus 12x plus 9 is equal to 0. Therefore, 3 into x square minus 4x plus 3 is equal to 0. Therefore, 3 into x minus 3 into x minus 1 is equal to 0. Therefore, x is equal to 3, 1. F double dash of 3 is equal to 6 into 3 minus 12 is equal to 18 minus 12 is equal to 6 is greater than 0. F double dash of 1 is equal to 6 into 1 minus 12 is equal to 6 minus 12 is equal to minus 6 is less than 0. Therefore, the function f of x has a local maxima at x is equal to 1 and local minima at x is equal to 3. the local maximum value of f of x, f of 1 is equal to 1 cube minus 6 into 1 square plus 9 into 1 plus 15 is equal to 1 minus 6 plus 9 plus 15 is equal to 19. And the local minimum value of f of x, f of 3 is equal to 3 cube minus 6 into 3 square minus 9 into 3 plus 15 is equal to 27 minus 54 plus 27 plus 15 is equal to 15. Example 2. Find two numbers whose sum is 24 and whose product is as large as possible. Solution. Suppose the two numbers are x and 24 minus x. Their product p of x is equal to x into 24 minus x is equal to 24x minus x square. P dash of x is equal to 24 minus 2x. Now p dash of x is equal to 0. Therefore 24 minus 2x is equal to 0. Therefore x is equal to 12. Therefore p double dash of x is equal to minus 2 is less than 0. Therefore p double dash of x at x is equal to 12 is equal to minus 2 is less than 0. P of x has the maximum value at x is equal to 12. For x is equal to 12, the product is as large as possible. 24 minus x is equal to 24 minus 12 is equal to 12. Therefore, the required numbers are 12 and 12. Example 3. Prove that the radius of the right circular cylinder of greatest curved surface area which can be inscribed in a given cone is half of that of the cone. Solution. Let OC is equal to R be the radius of the cone and OA is equal to H be its height. Let a cylinder with radius OE is equal to X inscribed in the given cone. The height QE of the cylinder is given by QE upon QA is equal to EC upon OC. Since triangle QEC is similar to triangle AOC, or QE upon H is equal to R minus X upon R, or QE is equal to H into R minus X upon R. Let S be the curved surface area of the given cylinder. Then S is identical to S of X is equal to 2 pi XH into R minus X upon R is equal to 2 pi H upon R into Rx minus X square. S dash of X is equal to 2 pi H upon R into R minus 2X. S double dash of X is equal to minus 4 pi H upon R. Now S dash of X is equal to 0 gives X is equal to R by 2. Since S double dash of X is less than 0 for all X, S double dash of R by 2 is less than 0. So X is equal to R by 2 is a point of maxima of S. Hence, the radius of the cylinder of greatest curved surface area which can be inscribed in a given cone is half of that of the cone. Maximum and minimum values of a function in a closed interval. Let us consider a function f given by f of x is equal to x plus 2, where x belongs to open interval 0, 1. Observe that the function is continuous on open interval 0, 1 and neither has a maximum value nor has a minimum value. Further, we may note that the function even has neither a local maximum value nor a local minimum value. However, if we extend the domain of f to the closed interval 0, 1, then f still may not have a local maximum or minimum values, but it certainly does have maximum value f of 1 is equal to 3 and minimum value f of 0 is equal to 2. The maximum value 3 of f at x is equal to 1 is called absolute maximum value, which means global maximum or greatest value of f on the interval closed interval 0, 1. Similarly, the minimum value 2 of f at x is equal to 0 is called the absolute minimum value, which means global minimum or least value of f on closed interval 0, 1. Consider the graph given in figure of a continuous function defined on a closed interval a, d. Observe that the function f has a local minima at x is equal to b and local minimum value is f of b. The function also has a local maxima at x is equal to c and local maximum value is f of c. Also from the graph, it is evident that f has absolute maximum value f of a and absolute minimum value f of d. Further note that the absolute maximum or minimum value of f is different from local maximum or minimum value of f. We will now state two results without proof regarding absolute maximum and absolute minimum values of a function on a closed interval I. Theorem 5. Let f be a continuous function on an interval I is equal to closed interval a, b. Then f has the absolute maximum value and f attains it at least once in I. Also, f has the absolute minimum value and attains it at least once in I. Theorem 6. Let f be a differentiable function on a closed interval I and let c be any interior point of I. Then, number 1, f dash of c is equal to 0 if f attains its absolute maximum value at c. Number 2, f dash of c is equal to 0 if f attains its absolute minimum value at c. Working rule. Step 1. Find all critical points of f in the interval. That is, find points x where either f dash of x is equal to 0 or f is not differentiable. Step 2. Take the endpoints of the interval. Step 3. At all these points listed in step 1 and 2, calculate the values of f. Step 4. Identify the maximum and minimum values of f out of the values calculated in. This maximum value will be the absolute maximum, that is greatest value of f, and the minimum value will be the absolute minimum, that is least value of f. Example 1. Find the absolute maximum and minimum values of a function f given by f of x is equal to 2x cube minus 15x square plus 36x plus 1 on the interval closed interval 1, 5. Solution. We have f of x is equal to 2x cube minus 15x square plus 36x plus 1. Therefore, f dash of x is equal to 6x square minus 30x plus 36 is equal to 6x minus 2 into x minus 3. Note that f dash of x is equal to 0 gives x is equal to 2 and x is equal to 3. F double dash of x is equal to 12x minus 30. We shall now evaluate the value of f at these points and at the endpoints of the interval closed interval 1, 5. That is, at x is equal to 1, x is equal to 2, x is equal to 3 and at x is equal to 5. So, f of 1 is equal to 2 into 1 cube minus 15 into 1 square plus 36 into 1 plus 1 is equal to 24. F of 2 is equal to 2 into 2 cube minus 15 into 2 square plus 36 into 2 plus 1 is equal to 29. F of 3 is equal to 2 into 3 cube minus 15 into 3 square plus 36 into 3 plus 1 is equal to 28. F of 5 is equal to 2 into 5 cube minus 15 into 5 square plus 36 into 5 plus 1 is equal to 56. Thus, we conclude that absolute maximum value of f on closed interval 1, 5 is 56, occurring at x is equal to 5, and absolute minimum value of f on closed interval 1, 5 is 24, which occurs at x is equal to 1. Example 2. An Apache helicopter of enemy is flying along the curve given by y is equal to x square plus 7. A soldier placed at 3, 7 wants to shoot down the helicopter when it is nearest to him. Find the nearest distance. Solution: for each value of x, the helicopter's position is at point x, x square plus 7. Therefore, the distance between the helicopter and the soldier place 3, 7 is square root of x minus 3 whole square plus x square plus 7 minus 7 whole square. That is square root of x minus 3 whole square plus x raised to 4. Let f of x is equal to x minus 3 whole square plus x raised to 4, or f dash of x is equal to 2 into x minus 3 plus 4x cube is equal to 2 into x minus 1 into 2x square plus 2x plus 3. Thus, f dash of x is equal to 0 gives x is equal to 1, or 2x square plus 2x plus 3 is equal to 0, for which there are no real roots. Also, there are no endpoints of the interval to be added to the set for which f dash is 0. That is, there is only one point, namely x is equal to 1. The value of f at this point is given by f of 1 is equal to f of 1 minus 3 whole square plus 1 raised to 4 is equal to 5. Thus, the distance between the soldier and helicopter is square root of f of 1 is equal to square root of 5. Note that square root of 5 is either a maximum value or a minimum value, since square root of f of 0 is equal to square root of 0 minus 3 whole square plus 0 raised to 4 is equal to 3 is greater than square root of 5. It follows that square root of 5 is the minimum value of square root of f of x. Hence, square root of 5 is the minimum distance between the soldier and the helicopter.